Selfie segmentation is one of the most exciting applications of image segmentation. Not only can I replace my background with an image by a click of a button, but I can do the same thing with a video background loop. And not only that, but in this tutorial, you learn to do all of this, plus you learn to blur out the background and also control the amount of blur using just your webcam. And then you'll also learn to create this cool desaturation effect where the background is black and white and I'm in color. And not only will you learn to do all of this in this single tutorial, but I'll teach you how to apply this on images as well as on real-time video feeds running on a CPU. We'll accomplish this using a library called MediaPipe. The approach that we'll use is a state-of-the-art approach that's also used on Google Hangouts. And at the end, I'll show you how you can use MediaPipe with OpenCV to convert any image to its transparent version. So if you're excited for this tutorial, let's get started. So before we go to the code, I'm going to briefly cover image segmentation and its various types and some other theoretical details. If you want to skip this part, you can do that by going to the timestamps in the description below. Alright, so let's start with a brief description of image segmentation. So if you're somewhat familiar with computer vision, you might have come across image segmentation, where just like object detection, you're trying to localize objects in the image, and instead of drawing boxes around it, you're doing approximately the same thing, but you're trying to segment out the exact outline of the object. In other words, in segmentation, you're trying to divide the image into groups of pixels based on some specific criteria. So an image segmentation algorithm will take an input image and output groups of pixels. Each group will belong to some specific class. Now the task of image segmentation can be divided into several categories. Let's understand each of them. First off, we have semantic segmentation. In this type of segmentation, our task is to assign a class label, example a pedestrian, car, or rural tree, etc., to every pixel in the image. As you can see, all the objects in the image, including the buildings, sky, sidewalk, are labeled by a certain color, indicating that they belong to a certain class. For example, all cars are labeled blue, people are labeled red, and so on. It's worth noting that although we can extract any individual class, for example, I can say extract all cars by telling the algorithm to look for blue pixels, but we cannot distinguish between different instances of the same class. For example, you cannot reliably say which blue pixel belongs to which class. Now let's look at instance segmentation, which is another common category of segmentation. Here, the goal is not to label all the pixels in the image, but only label some selective classes, for example, which the model was originally trained on. Here, we are looking just for the cars and pedestrians, so only those will be labeled. As you can see in the image, the algorithm is ignoring the roads, the sky, building, etc. So here we're only interested in labeling specific classes. One major difference in this approach is that we're also differentiating between different instances of the same class. For example, you can also tell which pixel belongs to which car and so on. Next up, we have panoptic segmentation, which is a combination of both semantic segmentation and instance segmentation. So here two things are happening. A, we are labeling all the pixels in the image just like semantic segmentation. And B, we are also differentiating between the different instances of the same class. So we can tell which pixel belongs to which car, etc. Finally, let's talk about saliency detection. Now, don't be confused by the word detection here. Although saliency detection is not generally considered as one of the core segmentation methods, but it's still essentially a major segmentation technique. So here the goal is to segment out the most salient or the most prominent things in the image. The most prominent things are those which stand out. For example, for this image, the things standing out are the cars or maybe the building. So that's why they are labeled white and the rest of the things are labeled black as the background. Let's take a look at another example of this saliency detection. So for example, in this image, the thing that stands out is the cat and the rest of the background is ignored. Now that we have gone over the basic segmentation techniques, let's try to understand what selfie segmentation is. Well, obviously, it's a no-brainer. It's a segmentation technique that segments out people in images, just like this. You might think, how is this different from semantic or instant segmentation? Well, to put it simply, you can consider selfie segmentation as a sort of a mix between semantic segmentation and saliency detection. What do I mean by that exactly? Well, so take a look at the example output of selfie segmentation on these two images. In the first image, the segmentation is done perfectly and every person is on a similar scale and stands out in the image. Whereas in the second image, the woman is prominent and it's standing out from the rest of the crowd. So only she is segmented out correctly, while her colleagues in the background are not segmented properly, as you can see here. This is why this technique is called selfie segmentation. It tries to segment out prominent people in the image. So this is why this technique is called selfie segmentation. Not only does it tries to segment out people, but it tries to segment out people that are standing out or are prominent in the image. This is why this technique is sort of a mix between saliency detection and semantic segmentation. Now you might think, why do we even need to use another segmentation technique? Why not just segment out people using semantic or instant segmentation methods? Well, actually we could do that using models like Mask RCNN or DeepLab v3 and other state-of-the-art models. But there's a problem. These models also give state-of-the-art results, but they are actually really slow and they aren't a good fit when it comes to real-time applications, especially using CPUs. This is why a selfie segmentation model is specifically designed to segment out people while also running at real-time speed on a CPU and other low-end hardware. The model we'll be using is built on a slight modification of the MobileNet v3 model. This algorithm contains several algorithmic innovations for maximum speed and performance gains. To understand more about these algorithmic advances, I recommend that you read this Google AI blog post on this model. So what are the practical applications for this technique? The most common practical application is video conferencing. In fact, Google Hangouts is actually using a modification of the same model that we'll be using today. So yeah, it's a state-of-the-art approach. Besides video conferencing, there are several other use cases for this model that we're going to go over today. The library or the module that we'll be using is called MediaPipe. MediaPipe is a cross-platform tool that allows you to run a variety of machine learning models in real time. It's designed primarily for facilitating the use of machine learning in streaming media. Alright, that's enough of the theory and let's start with the code. Alright. To get started, you first need to download this fully documented Jupyter notebook that can be found from the link in the description below. And let's start with the code. Alright, so the first thing that we need to do is install this library called MediaPipe. You can easily do that by doing pip install MediaPipe. After you're done with that, you'll have this library and then we can import MediaPipe as MP. And then we can use this alias to call off the models. Alright, other than that, I'll be using OpenCV, NumPy, Matplotlib, and the other Python default libraries, which is the OS and the time library to calculate the FPS. Okay, so let's import the libraries when we're done with that. And now what we're going to do is initialize the MediaPipe segmentation class with this line of code. And then I'm going to set up the segmentation function with this line of code. So when setting up the segmentation function with MediaPipe, we have two options. So we have two different segmentation models. So the first is the general model and the next one is the landscape model. The difference between the two is how they internally work. So the first is the general model, which resizes the image into 256 by 256 into 3, and the other is the landscape model, which resizes the image into 144 into 256 into 3. As you can see, the landscape model internally resizes input and compresses it a lot more than the general model. So it will be a bit faster and it's more suited towards images that are landscape shaped. So this is the basic difference between the two. The general model will generally perform a little bit better depending upon the aspect ratio of the image. And you can switch between both of these models by passing 0 or 1 in this constructor function. So by passing in 0, you'll be using the general model, which is the default. And by passing in 1, you'll be using the landscape model. By default, I'm using the general model for this tutorial. So this is initialization and this is the setting up of the segmentation function. So I'm gonna set up this function right now by running this piece of cell. Now the segmentation function is all set up. I'm gonna read up my image, which is going to be this sample image using OpenCV. So I'm doing cv2.imread, which is going to read up and sample image from OpenCV. I'm going to set out the figure for displaying a matplotlib image, and then I'm using matplotlib to display this sample image. So this is the title. I'm shutting off the axis, and this is the general imshow function and reversing the channels so that BGR images that are loaded by default in OpenCV are displayed properly in matplotlib. So this is how the display is done. Now this is the sample image that we'll be working on for the first application. So I'll be going over 4 applications today. So this is the first one, image background replacement. Then we'll be going over the background blur, image desaturation, and then finally we'll learn to convert image into transparent. All right. So the first part, what I'll be doing is I'll be showing you bit by bit how this process happens, and it's pretty simple. So the first thing that I need to do is convert this image into RGB. So by default, OpenCV loads up image in BGR, but MediaPipe accepts images in RGB format. So this is why I'm gonna do this color conversion by using the function convert color, passing in the sample image and telling it what sort of color conversion do I want. I'm telling it that I want BGR images to be converted into RGB. So this is how the color conversion is done. After I have the RGB image, I'm gonna pass in directly in the segmentation function by calling segment.process. So remember, we initialize the segmentation as segment object, and then we can call dot process on this object to perform the segmentation. So this is in this line, the whole segmentation is happening. So after the segmentation is done, we'll get probability map. So this map will tell you where the model thinks the person is present. So remember, this is selfie segmentation. The model will only be highlighting where it thinks the person is present. Okay. So I'm then initializing the figure size for displaying, and then I'm displaying both the original image and the segmentation map. Let's see the results. So this is the original image, and this is the probability map. As you can see, this is not exactly a black and white image. It contains some gray areas too. So these are some areas, and you'll probably see more gray areas where the boundary of the image is present, the boundary of this person. So these are the areas where the model is not exactly sure if this is the background or is this part of person, of the foreground. So this is where we can do some sort of thresholding to either convert this gray part into black or white, depending upon how confident we want the model to be. So this is where the thresholding is done. So we have a probability map in which we have this output image, which is the same size as the original input. And for each pixel, we have a value ranging from 0.00 to all the way to 1, which signifies how sure the model is. The closer the value is to 1, the more positive the model is that this particular piece of pixel is the foreground or belongs to the person. All right. So this is where all the thresholding is happening. Remember in the above code where we did segment.process and we got the probability map in this object. And then what we did was result.segmentation mask where we got this probability map. So by doing dot segmentation mask, we will get this probability map, which we displayed above. Now what I can do is do this sort of comparison. Now by doing this comparison, I'm telling the model to replace all those places where it's 90% or plus positive with 1 and all the places where it's less than 90% confidence with 0 values. So this way I'll get a binary mask where there will be a 0 in all the places where the model thinks it's the background and 1 in all the places the model thinks the person is present. And obviously the model will have a 90% or plus positive that it's a person, otherwise it will be set to 0. So this is how I'm setting all those gray areas either to white or black depending upon how confident those values were. All right, so this is finally the black and white binary mask that we have, and this is all we need to do all sorts of things from now on, either to replace the background, smooth out a background, or get a transparent image, or do any sorts of thing. So this is the final binary mask that we need. And as you can see, the code is really simple. It's just 2 or 3 lines of code. The other pieces of code is just for displaying purposes or visual purposes. All right, so now that I have the binary mask, what I will do first is replace this black and white mask with a white background. So I'll replace this background of this image with a simple plain white background. So for that, what I need to do is replace this background with 255. 255 represents white and 0 represents black when you're working with unsigned 8-bit images. Alright, the first thing that I need to also do is convert this binary mask into a 3-channel image so that I can use this function. So this is the function where I'm saying np.where binary mask, a sample image and 255. So what this np.where function does, it accepts 3 arguments. The first argument is a binary black and white mask. The second is the foreground. And the third is the background. So how this works is that it uses the mask and checks wherever the white is present. So this is the white. And what it does is replaces the foreground with the white. So the foreground is probably this image, which I am passing the original image. So it will replace all the white parts with this piece of original image. And then what it will do is replace the remaining black parts with the third argument. Now, as the third argument, I'm passing a single 255 constant. And what it will do is replace all the black parts with this constant 255, which is white value. So the background will become white and the foreground will retain its original content. So this is what np.where does. But to run np.where, what you need to do first is have a 3-channel binary mask, and which is the reason I'm calling this function. So it's stacking the binary mask 3 times to create a 3-channel image. So this way, all these 2 images will have the same channels, and this is a requirement to run this np.where function. So now we have the output image, and finally we'll see the results of this output image. So this is the result. As you can see, it's pretty good for this sample image. This is the original image, and we have replaced the background, which is a constant white, with this image. And now the exciting part is that all I need to do to replace this white part with an actual background, a different background, is just replace 255, which I put here, with just another image. So I'll load up another background image, which is from a media folder. And you'll get this folder obviously when you download the code. And then what I just need to do in the code above is just replace this 255 with another image. So this background image. And once I do that and I run this, I'll get these results. So as you can see, once you have this binary mask, it's pretty simple. You just create its 3-channel version and just replace a background with anything, either 255 constant or any other color or just another image. It's simple as that. So this is the whole process. Now what I'll do is copy all the code above and create a function out of it. So right now I'll have this function, modify background. And in this function, I'm going to accomplish 4 things. Function, a piece of code to replace the background with any other image, a piece of code to blur out the background, a piece of code to desaturate the background, which means replace the background with its black and grayscale version, and to leave out the original person as it is. And then a piece of code to convert the image in transparent version. So let's take a look at this function. So as I said, all of this code is already what we've covered above. The only difference here are these conditions here. So these are the conditions that are controlling what sort of manipulation we want to perform on the image. And I'll get over all of these 3 when I'm covering these 3 applications below. As you can already see, it's just a difference of 1 or 2 lines of code. And that's the best part about this. You can just replace 1 or 2 lines of code and you got another application. That's how cool this is. All right. So yeah, I'll just briefly go over these variables. So the blur is controlling the amount of blur, which I'll cover later on. And the display, when the display variable is set to true, we'll see the image displayed out by matplotlib. Otherwise, when the display is set to false, the output image will be returned. And I'm doing some sort of manipulation and data conversion, so we can use imshow function to display the output. Otherwise, the output won't be displayed with the imshow function because of the data type will mess up. Anyways, so the reason I'm controlling this is that Whenever I'm working with images, I want to display them and see the results. But whenever I'm working with videos, I don't want to display the results each time a frame is read up with matplotlib, but I just want the results to be returned so that I can perform the iterative loop when I'm working with videos. So this way, I'll set display equals to true whenever I'm working with images, or false whenever I'm working with videos. So this single function will work on images and videos, and will also control the type of application I want to work, controlled by these if conditions. And so this is the main variable which you should be concerned about. This is the threshold which will control how confident you want the final segmentation mask to be. If you're seeing a lot of background, then you can increase this threshold, and if you're seeing your face, part of face being replaced by the background, then you can decrease the threshold. So this threshold will control the segmentation output mask. All right, the rest of the code is pretty much same. I mean, I've already gone through all of it. So let's initialize this function, and once we've done that, we can test it out on multiple images. So that's what I'm doing below here. So I'm reading up a sample image, and then I'm calling the function modify background and passing it the image, and I'm passing it a sample background image and telling it the method I want is change background, which we've just covered. All right, let's run this. So for this image, the result is pretty good. Let's check another image and a different background this time. And I've increased the threshold. So as you can see, this is the result for this one. Again, for images, the result is pretty realistic. All right. So as you can see, there's still some outline here that you can see, maybe a brief outline. You can adjust the threshold and see different results. Let's run on another image. So for this image, we're seeing this result pretty good. All right. So now we have seen the work of this model on images. Let's test it out on a video, on a real-time video webcam feed. For that, what I'll be doing is first I'm gonna read up the camera object, set up the camera video capture object. Then I'm gonna set up the width and height of the frames. And then I'm gonna specify a background folder. And what I'm gonna do is read up or store all the background images in this list. And then I'm checking to make sure if the camera is initialized properly. And if it is, then I'm reading frame in every iterative loop. And I'm checking to make sure if the frame was read correctly. If it was not, then I'm skipping the whole loop. The continue, goes back to the start. And then I'm laterally flipping the frame because by default OpenCV inverts the image horizontally by default, and it's not a good effect. I want a mirror image when I see the video. So that's why I'm just flipping the frame horizontally, and this is where the whole modification is happening. So I'm running the modify background, passing it the frame, passing it the background image. As you can see, the background image will automatically update depending upon what the background image index is. So at the start, the index is set to 0, and whenever the user presses B, the index updates. And whenever the index updates, it chooses a different background image on this list. So this is how the background dynamically updates whenever the user presses a B button. And then I'm setting a 40% threshold, display is set to false because obviously I want to work with videos. As I previously explained, the method is change background. So that is all I need for this piece of code. And then what I'm doing here is just calculating the FYP. Not FYP, but FPS. Okay, so the frames per second, how many frames per second, what's the processing speed of this code, that is what I'm displaying here. So to do that, all you need to do is initialize the time and then calculate the time when all the processing is done, and then you just divide by 1 the total time that it took, and you get the FPS. And then that's what I'm displaying the FPS using put text CV to put text, displays the text on the screen. And then I'm updating the timer and then displaying the results with cv2.imshow. And then I'm waiting for the user to press any keyboard button, and whatever the button the person presses, it's stored in this k variable, as in its actual ASCII value. And if the user presses the escape button, which has the ASCII value of 27, I want to break out of the loop and I want to release the camera and destroy all the windows. All right, so this is the whole code, whole video code, and let's run this and see it in action. Okay. So this is the result that you will see when you run this code. As you can see, whenever I press the B button, it's replacing the background. As you can see, my sheet is being segmented out. And the reason for that, this is the selfie segmentation. It's not meant to segment out my chair too, but it's, so yeah, this is the reason. Still, you can, modify these results by changing that threshold value. Right now, it's set to 40%. So you can change that 40% value and see different results. As you can see, the FPS is pretty high. We're getting a 30 plus FPS here for this video feed. And I also checked the results with my Sony A64 camera previously, and it were even better than this. But the FPS got slower because the larger the input images are, the more time it's going to take to process and display. So this will also work in real time with higher end cameras, but it will take more time to process that. All right, I'm going to press the escape button now and exit out of this. Now I'm going to see a video on video background replacement. So I'm going to replace this video with another video loop. And the code for that is, pretty simple actually. Just so I'm doing this sort of thing. So as you can see, we have the original video feed that I'm using with camera read object, and I've initialized another camera object here above, which is responsible for reading the video. So here I'm reading frame by frame the actual video feed, and here I'm reading the stored background video feed. So this will be read in a loop. So this is the loop happening here. So each time I read a new frame, I'm incrementing a counter variable, and the counter variable is named as background frame counter. So I'm appending 1 each time I read a new frame. And this makes sure that whenever I reach the end of the video, I can reset the video at the start. So this way, I don't have to run out of the frames. So I don't need a really long video, like I don't need an hour-long video. I can just have a 10-second video and loop it until I want to exit out of the whole video. So this is what's happening here. When the video reaches the last frame, I'm resetting the video by using this piece of code, background video.set. I'm using the video property. This property controls the frame and setting this frames to 0. So this way the video will now be read again from the first frame, and then setting the counter back to 0 again. So this is the only thing that's probably new here, and the rest of the piece of code, it's the same. So let's see the results for this one. So yeah, this is the result that you will see. The video loop is behind me, and whenever the video loop ends, it's gonna start again. So you can test this code out from by yourself, and I will exit out of this video. All right. So this was the whole background replacement, and that was the first application. Now let's go over the rest of the applications. As I said, we've already created the whole code to run all of these 4 applications, and the only thing that I will need to change is set method equals to blur background. So the method variable is the only thing that I will need to change, and the whole code will now work as a background blurring mechanism. And to accomplish that, I'm using a Gaussian blurring. So Gaussian blurring is a very common method in OpenCV to smooth out the background. So you will get something like this. You'll get this image and blur out the background. And you can also control the amount of blur that you want. So there's another variable called blur. So this is how I'm controlling this. The blur is equals to 51. The amount of background blur will be less. And if I set this to 91, it will be the effect magnitude will be higher. So this is how I can control the amount of blur. Let's check it out on some sample images first. So this is the original image, and this is the blurred version. So as you can see, the smoother out version looks pretty good. And let's check it out on another image. And this is the result for this one. And finally, another image. So this is the blur result of 51. If I take it up a notch, like put it like 91 or something like that, you will see the blur amount, it's a lot high. So the magnitude of blur is a lot high. So I'm setting it back to 51. It's more aesthetically pleasing. So yeah, this is the modify blur. Similarly, I can run this background blur on videos. I'll just set this to 0, and then, by the way, one thing that I would tell you that this Gaussian blurring, when you do that, the speed slows down a bit, because Gaussian blurring itself is a expensive operation. So yeah, as you can see, this is pretty good considering that you only have a single webcam, and to accomplish such sort of blurring effects, normally you would need an expensive DSLR or a Sony camera or mirrorless camera or something like that. So you can and now you don't even need to have separate lenses or apertures to control, like the blur amount. You can just tune out the Gaussian blur value and it will control the blur amount. And all of this is running in real time on a CPU. So considering all that, I'll say it's a pretty good application. All right, the code again, like I said, is the same code, just the thing that's different here is the method, blur background. Now we'll take a look at the desaturation effect, and all you need to do is choose the method desaturate background. By the way, I should explain how the Gaussian blurring is happening in the code above, function above, in the main function. So whenever you call the blur background function, so this function gets called, the image goes in, and then you have a kernel amount. So the kernel controls the magnitude of blur, and then there's also this constant value that also utilized in the Gaussian function. So this is what's just happening, and then at the end we just instead of we do the same thing that we're doing above, but we only think different here is that we're passing it this blurred version. So that's all that's happening here when you call blur background. And then when you call desaturate background, what happens is that you convert the image into its grayscale version. So it's black and white version, not exactly black and white, but the grayscale version where you don't have any color. So then after the image is converted into grayscale, you replace that grayscale version with here. So notice the only thing that we're doing in all of these three applications is replacing the third variable with something new. So here we have this background image, here we have this blurred version, and here we have this grayscale version. So the background will be replaced by the original image's grayscale version, and the foreground or the person's part will retain its original value. And by the way, this since the grayscale image is in 2D, it's a single channel image, we'll be stacking it 3 times to create a 3-channel version so that np.where function works correctly. And then finally, at the end, we'll have this transparent background function. And for that, you don't even need to do anything. All you need is a black and white mask, which is already provided. But only thing we will do here is the thing we want is that black and white mask to be 0 or 255 and have the data type unsigned it. So it's just a data type conversion problem. So that's all that's going to happen when you convert an image into transparent. But there's another bit of technicality which I will cover when I'm talking about the transparent conversion part. But the only thing that you need to remember is that the only thing we're doing here is returning the output image, and the output image is just a black and white binary mask. But the difference is that instead of zeros or 1, we'll have values all the way from 0 to 255. So because it's a black and white, so we'll have 0 for black and 255 for white. So that's all that's happening in all of these 4 functions. So now let's run the desaturation function and see the results. So okay. So this is the desaturation function. It's looking good. Another image, pretty good. And then another image. So yeah, it's pretty cool. So now let's run this function on a video. The same code, it's the same code. That's the best part about this tutorial. It's the same code for different applications. So what's the problem here? I think it's okay, problematic. Oh, so yeah, I didn't. Let's start with that. I have that box now. Okay, okay, yeah. So as you can see, it's pretty good. The desaturation is happening here, and it's running in real time with a high FPS. So I'm not displaying the FPS here. Okay, let me just uncomment that part, and then I'm gonna run this. And yeah, the FPS, as you can see, 30 plus FPS, grayscale version. It's a pretty cool effect here. Okay, so that's the desaturation. And finally, the conversion part. So this method will obviously, the limitation for this method is that it will only work when you want to convert image that contains a person to its transparent version. It will not work for other objects. For that, you will need to have a deep learning based saliency detection function. Maybe I'll cover that in a future tutorial. And the saliency detection is another great segmentation technique. Anyways, so what will happen is that we'll create an alpha channel. So in OpenCV, you normally work with two sorts of images. You work with grayscale images and you work with color images. But there is a third type of image. In grayscale image, you have a single channel image which has values ranging from 0 to 255. And in color image, you have three channels: a red channel, a blue channel, and a green channel. And all of these channels stacked together creates the illusion of any color that you want. So this is the BGR or the RGB color system that you have. And if with the transparent image, the difference is that you have this fourth channel called the alpha channel. And this alpha channel is a binary map. It's not exactly binary map, but it's a map that has values from 0 to 255. It's a single channel map, and this map controls what part of the image should be shown and what part of the image should be replaced by any background that the image takes up. So this is what happens here. So all we need to do is add this binary mask that we get with the segmentation technique and add it to the image, and then save it to the disk as a CV with the cv2.imwrite function. So this is the whole code. We're specifying the path where the image is present. We're reading up a sample image, and then what I'm doing is modifying the background by passing a method transparent background. So this is when the image will be converted to its transparent format. And then when the image is converted to its transparent version, what I'm going to do is save the image as .png. Remember that you need to save image as .png only. You don't need to save the image as .jpeg or JPG. The only extension you need is .png. And this way the image will be written as transparent, because all the processing or all the stuff is done when you run this function above. So let me go over this function above again. So yeah, so this is the function. Okay. Oh yeah. All right. So remember this piece of line where what I did was I did two things. The first thing that I did was convert the image that was in zeros and ones to 0 and 255. So this is the format that you want. The other thing that I think I forgot to explain was that I was stacking the normal BGR image with another fourth channel with this mask. So this mask is behaving as the fourth alpha channel. And this is how we are creating the transparent image. And this is all done when you return this output image. So the whole thing is happening in this single piece of line of code. You're stacking the original colored image with another channel, and this is the alpha channel. Basically, it's just the same mask multiplied by 255, and all the work is done in this line of code. All right, so let's return to the code. So once you got the transparent background image, you just save it with the imwrite function, and you've got the stored transparent version saved. All right, I'm gonna show you the results after I run this function. So the image with transparent background is successfully stored in the disk. So let me show you the result. So once you run this code, you'll see the output result saved in this output folder. And once I open up this image, it will be a transparent version. So as you can see, the background is gone. The default background is being taken up by this media displayer. So this is how you convert any image to its transparent version. So, and there are some other resources, interesting resources that you can go over and from this section. So that is all for this lesson. If you enjoyed this tutorial and if I helped you in any way, make sure to subscribe to this channel, and a lot of other exciting tutorials are coming up. So I'll see you then. Bye.